termasuk alumni generasi awal ya Pak ya.
Generasi kedua. Ya.
Generasi kedua ya, alhamdulillah ini luar biasa. Dan beliau menempuh pendidikan ya di S1 di IPB University angkatan apa ya Pak? Jadi angkatan
33, 96.
ya, 5 tahun sebelum saya berarti ya. Saya masih SMP berarti di Pak Parada. Jadi beliau sudah masuk di IPB tahun 96 menyelesaikan S1-nya dengan waktu itu dibimbing siapa Pak Parada ya?
Saya tuh waktu itu ngerjain film sama
Pak
Pak
Akhir ya.
Ya,
ya. Alhamdulillah Pak Akhir juga sudah jadi profesor belum lama ini.
Ya, makanya saya senang juga. Ya. Alhamdulillah.
Kemudian beliau menyelesaikan S2 di Theoretical and Mathematical Physics di Universitas Indonesia di bawah bimbingan Pak siapa Pak?
Pak Terry dan Pak Anto.
Profesor Terry Mat sama Pak
Anto.
Pak Anto Sulaksono.
Sulaksono, ya.
Ini dua orang hebat juga di UI ya. Kemudian berarti sebelum Haryo atau setelah Haryo ya?
Setahun hari duluan sama Pak Tony. Pak
Haryo ya. Oke. Baik, kemudian S3 beliau selesaikan di Theoretical and Mathematical Physics University of Glasgow di Adelaide, Scotland ya, dengan publikasi beliau cukup banyak dan saya akan mention 3 saja. Salah satunya adalah yang terbaru ini, Effects of Neutrino Magnetic Moment and Charge Radius Constraints and Medium Modifications of the Nucleon Form Factors on the Neutrino Mean Free Path in Dense Matter. Ini sepertinya cukup menarik karena membahas tentang neutrino yang saat ini salah satu kandidat dark matter mungkin ya Pak ya. Mean free path in dense matter ini sepertinya nanti larinya ke statistical physics ya Pak ya, atau gimana?
Enggak.
Ya?
Okay. Perhitungan teori asli ya.
Oke. Ini sudah dipublish di Nuclear Physics A ya tahun 2022. Kemudian di Physical Review D dengan judul Count Form Factor in Holographic QCD. Oke. Jadi ini Count ini salah satu juga yang sedang Pak Terry juga masih menggeluti ini ya Pak ya. Count.
Iya, tapi Pak Terry banyak ngerjain Count photo production.
Tapi ini independen dari penelitian bersama beliau. Ini
sebenarnya bisa independen, bukan part.
Oke. Nah, kemudian ada juga dark matter and Meson properties anomalies in flavor dependent gaussimetry. Ini di Physical Review D tahun 2019. Jadi penelitian Bapak cukup variatif juga ya, mencakup QED tetapi tidak dengan partikel yang sama ya, jadi cukup cukup fleksibel begitu ya. Nah ini kemudian hari ini beliau akan bicara tentang partonic structure of hadron, emergent mass and structure. Jadi mudah-mudahan kita semua bisa terinspirasi oleh talk beliau hari ini. Saya rasa karena sudah masuk waktunya, saya mohon izin untuk memberikan waktu kepada speaker kami hari ini, ya, Bapak Parada Hutauruk, untuk memberikan talk-nya, oke? Dengan topik.
Saya bisa share screen.
Oke, ini partisipannya sudah mulai banyak nih Pak. Oke, silakan. Saya coba untuk mohon bisa diberikan sebagai co-host Pak Parada.
Dari gimana?
Coba apa saya bisa? Ya. Oh ya. Oke.
Saya
coba
bisa
Pak.
share.
Coba Pak, silakan.
Please wait. Okay. Kok saya nggak melihat ini ya? Okay. Can you see?
Yes, very good. Jelas.
Okay. Ini langsung aja apa? Saya tunggu.
Silakan Pak, langsung dimulai saja.
Oke, oke. Saya pakai ini ya bahasa Inggris ya, nggak apa-apa ya.
Lebih baik Pak. Ya.
Mudah-mudahan mengerti ya. Mahasiswanya. Oke. Okay. First of all, I thank you very much for inviting me to give a talk and then come back back to my university, my former undergraduate former university, and I also thank you, Professor Hussein Alatas, Dr. Dodi, and Dr. Dedi Yesi for inviting me to give a talk in our department. And also I congratulate Professor Tony has been awarded the professorship recently. Okay, without wasting the time, I start. The title of my talk is about the parton structure of the hadron, which is related to the emergent mass and the structure of mechanism. Okay, so the parton is the hadron has a has a structure, which is the parton contained by a valence quark, we call it. There is a gluon inside, and also there is a C quark. So this I will elaborate later in my talk. So for the students who don't know me, my name is Parada Hutauruk. I'm from the Nuclear and Hadron Theory Group, Department of Physics and Radiations, Pukyong National University. This I presented is a collaborate with the Seng Ilnam, Antotin Thomas in Adelaide University, and Ian Claude in Argonne Laboratory. So yeah, before I start my talk, is this to understand the hadron structure, because in the experiment we don't know, we don't have a prior informations to understand what is the hadron structure. So sometimes the researcher is touch they said this they touch these the spheres, and then they said when they touch these, and they said is a snake, and then also when they touch another part of the body of the elephant, they said a tree, and someone said rope and everything. So this that we did for building to understand the structure of the hadron is very complicated, especially for baryon, which is has a 3 quark inside. So this is like an analogy for that one. So what we did is like this one, we're building, and they try to understand which this 11 or not in. So by using every model, lattice QCD experiment, or all that one, all informations to understand the hadron structure. So the outline of my talk today is I start briefly to explain about the building block of the matter in the standard model, because QCD is part of the standard model. And then I explain about the quantum chromodynamics, which is if you're talking about the hadron, quantum chromodynamics is a underlying theory to understand the hadron structure. And hadron structure, you cannot directly look at, as I mentioned before with the analogy, that we cannot understand the hadron directly, but we have another observable that we call it parton. To understand parton structure, we call it form factors, and then parton distribution function, and then also there's we call it general parton distribution. But in this talk, I just explain about the form factor and then parton distribution function, then how they are correlation each other. I will explain later more detail. At the end of my talk, I try to make it conclusions and outlook. Okay, this is the building block of the matter of the universe that we understand. If you look at the history of the universe, which is depend on the time for start from the inflations, is they started to depend on the time they, when the Big Bang heaven is temperature is very high, which is related to the high energy cosmic ray, and also in the LHC heavy ion collider, is the temperature is very high. So, and then depend on the time, is become create some structure formations, and then also dark accelerators dark energy, etc. And today it's become like this one. So all this process is depend on time. We can understand with the very simple with the quarks and leptons, and all the interactions between this, you call it up quark, down quark, stump quark, string quark, top quark, and bottom quark. And also the lepton has a electron, muon, tau, and a neutrino electron, neutrino muon, as we call it, and this neutrino tau. So all the interactions of these particles, they have a factor bosons, which is as a particle exchange, intermediate particles. You call it, if you electromagnetic, and then weak interactions, strong interactions. If you electromagnetic is using the gamma, and a weak interaction is a G boson or W boson, and also gluon. So all these interactions just only using these particles to explain this phenomena. History, we can explain some part of the history of the universe using this building block of the matter. And then if you want to, as you know, if you want to build some, to explain the sum system in the physics, you have to use in Lagrangian or Hamiltonian. But in standard model, Lagrangian standard model of the particle physics, you can write Lagrangian like this one. So in the standard model, gluon is a factor boson, as I mentioned before, has a spin 1, it carries a strong force, right? So gluon has an 8 type, interact among themselves, and there's also color charts. But if more complicated, you can also include the I said W and the G bosons, which is carrying force carrying particles. And then the Lagrangian, you can see here, is very complicated and long, very long. And also in this, there is a Higgs interactions, W and G bosons, which is carrying weak force. And also the most discovery, which is a Higgs boson, we can include it to the Lagrangian. So if you included that one, and then the Lagrangian become more complicated. So there's also, if you include the other particles like Higgs field, and also massive matters, massive particles, and also there's additional of the Lagrangian, you can add it to the Lagrangian standard model of particle physics. And also, if you wanted to include more complicated, again, if you took standard model, then matter particles interact with Higgs ghosts, virtual artifacts, which is from Higgs field. We can also include it, that one, which is field the interaction with the Higgs field. And there's a more complicated. You can see here, it's too long. And this, if you also include the Faraday-Popov ghost, which is needed to explain the scattering between the quarks, and then you can edit this some kind of interaction to the Lagrange to standard model, Lagrangian standard model, and then it become more complicated that I have shown before. Okay, so but there's a standard model, Lagrangian for the standard model, but we nowadays, because I'm focused to the hadrons, as I mentioned before, the hadrons is has a theory which is we call it QCD, which is underlying theory for the hadron structure, strong interaction, and now I focus to QCD, which is a strong interactions. Okay, this. If you want to talk about the interactions, you talk about the scale or the hadron size. If you look at this, I will show here's the picture, which is the atom, which is has a size is 10⁻⁸ centimeters, and the nucleus, if you go more, and then 10⁻12, and for the nucleon, the size is 10⁻13 centimeters, and the quark is has a size 10⁻13, and in the future, maybe you can we can find something which is smallest than quark, we don't know. Depend on the beam that we have, the luminosity that we have to find structure of the quarks. But until now, we believe that quarks is the fundamental particles, as I mentioned before, as a building block of the matter in universe. Here I emphasize again, we focus to QCD interactions of the quark inside the hadrons, which is the size is 1 Fermi, which is equal to 10 minus 15 centimeters. So before we talk about the QCD, here I explain about the properties of the QCD itself. So QCD is a fundamental theory of strong interaction, which is has a degree of freedom quarks gluon as a fundamental degree of freedoms. And QCD is a non-abelian gauge theory. Abelian gauge theory means it's not non-commutative theory. So if you want to the dynamics of this QCD, you can using the Lagrangian like this one. This the kinetic part, this the tensor, the strength tensor, which is content of the gluon and the gluon interactions with the electromagnetic too. So, but the difference between QCD and QED, as you know, in QED, which is electromagnetic interactions, gluon has a self-interaction between the gluons. So this make the structure of the hadron more complicated because the gluon interact each other. Also, we should consider that one. Here I just show you actually the Lagrangian of standard model that I explained before. You can just fit to 1 Mach, which is more simple that I explained before. Okay, this the other properties of the QCD. If you go to short distance scale, which is R 0.1 Fermi at large scale Q square. If you look at this, you have the energy or momentum transfer, and this the coupling, running coupling constant. So if you have a higher energy, it's become asymptotic here. So, but if you have a very small energy, you have a coupling is a very large coupling, then in this regime, you can only use a strong non-perturbative theory. But in this regime, you can use non-perturbative theory, which is why you use perturbative QCD in this regime, because the coupling is very small. And then with the small coupling, you can apply like perturbations in this regime. If you look at the scale, for the scale, if the small coupling of the running coupling constant, which is around this one. So the distance that we use in the using perturbative QCD. If you have a large coupling, and then this you can see here that this regime that you can using, you call it non-perturbative theory. This is well done, which is asymptotic freedom, which is get a Nobel Prize given to Gross, Politzer, and Wilczek. And hadron structure and QCD have two emergent properties. You call it confinement and dynamical symmetric breaking, or short, you call it DCSB. In the lower limit, which is a momentum Q squared below 1 GeV squared, and the large distance scale, which is R larger than 1 Fermi, QCD is governed by quark confinement. I will explain this later, how this apply to structure of the hadrons, and then dynamical chiral-symmetric breaking, which is emergent hadron related to emergent hadron mass EHM. This I call it this in this regime. You can so in this momentum and large this scale, you can use only non-partitive QCD regime. But you know that you cannot see the quark outside the hadrons, so all the hadrons are color singlets, and then which is a composed color quark and the gluons. Hadrons, it can be applied to baryons, which is a 3 quarks, and the meson with the quark and an antiquark. Okay, this is how QCD meet with the structure of the hadrons. QCD as underlying theory of the strong interaction, unfortunately unable to directly predict the structure of the hadron, as I mentioned before. So what the solution that we use to explain the structure of hadron? There is a two method that we can use. First of all is a lattice QCD, which is there's one method that you call it large momentum affected theory, which is LAMET. I didn't explain this in detail here, but if you're interested, you can go to this reference, which is Xiang Dongji, which is a very famous, which is suggested this method in lattice QCD. And the other thing is a QCD inspired model. What is it means the inspired model? It means, as I explained before, QCD has features, has properties, right? The confinement and dynamical symmetry breaking. And we try to build the model, if you call it inspired models, by mimicking feature of the QCD, which are a confinement and dynamical symmetry breaking. So in such model, we can use like an Angel model, Dyson-Swinger equation model, QCD sum rule, instanton model, covariant non-local chiral quark model, and then other chiral effective model. And this model, some of this model has a prediction for this form factor of the pion times the chi square against as a function of the chi square. And you can see here, the orange color is a Manuchik duality model. And this Huang relativistic, this the blue dust line. And this done using another model, relativistic model, which is here. And then also there's a QCD sum rule in the black color, which is dot line. And this Dyson-Swinger equation model, the red color here, is a prediction for this one. And this, the pink one is our prediction for pion form factor. This is the QCD inspired models that some prediction of some of the models which is predict the pion form factor. And also this I show you some calculation from the lattice QCD, but unfortunately you can see here the mass of the pion is 280 MeV, which is very high, which is a physical mass of the pion is 140 MeV. So to get the right calculation for lattice QCD, you have to decrease the mass, which is close to the physical mass of the pion, which is equal to 140 MeV. But these need more computations, but more computations mean more cost to calculate it, such kind of calculations. This form factor transition of the pion as a function of the chi square. About this one, I just took it from the Gerd Haber slide. He's a professor in Canada, and this one you can also more detail in the Bastian Brand 2013. Okay, there's properties of PCD and the size, the regime that we talking about, which is related to the hadrons. Now I want to talk about the particle structure of the hadrons that we know at the moment. This I show you just some picture, which is how the gluon, this gluon and the quark inside the hadrons. how their dynamics in, but this come from the latest QCD result, which is this calculated by Direct Line Weber in University of Adelaide. And this one, okay, now I try to explain the pattern structure of the hadron using, now I'm specifically choose the specific model, you call it confining NGL model. About this model, I will try to elaborate in this slide, in this page. Okay, but before we talking about the pattern structure of the hadron, I will show you, maybe you're asking what is a hadron, and then as in general, there is a hadron can be classified based on the quantum number. The hadron can have two families. The first one, you call it baryons, and the second one, the mesons. Baryon is, as I mentioned before, is composed of odd number of quarks, 3 quarks, and meson is made by even number of the quarks, which is 2 quarks, 1 quark, and 1 antiquarks. But there is a, if you saw this, the baryon is like this one. This a cartoon for the baryon. This is a cartoon for the meson, right? And this is for gluon. There's also glue balls, which is a gluon interaction. We assume that there is the particles made it by only gluon, and had this hybrid, and also the gluon and the quarks. There's a theta quark and a Hutauruk molecules. It's like this one. But all this we can classify to baryon and meson. And maybe you ever heard about the exotic hadron, which is composed more than the 3 quarks, which is a tetra quarks and pentaquarks. But all these things we can reclassify to baryons. More detail about this one, you can see this paper is a very old paper. It's 1964, but it's very useful to understand the types of hadron and their structure. Okay, now we focus the structure of the baryon. Right, the history of the internal structure of the baryon is 1980s. We understand that the proton structure made up by 3 quark, up and down quarks, is like this one. But forget it, the speed. But start from 90s and 2000s, we understand the proton structure, not only the valence quark, up and down, but there is contribution from their spin, gluon and C quark. So the picture is changed, it become like this one nowadays, which is more complicated. You can see here is a gluon decay to quark and an antiquark, and another gluon, which is this, the blue, the pairing red quark, you call it C quark, which is come from decay from the gluon to quark and an antiquark. And that happens in randomly inside the hadrons. So there is a contribution. So the valence quark, 3 valence quark, there is spin, gluon, C quark, and also, as I mentioned before, there is interaction between quark, gluon, and gluon. That's making this size, a small size. This is just only 1 Fermi, but the interaction inside this hadron is more complex and complicated. So but the important question is now, by know this one, how the valence quark, gluon, and C quark distribution to this baryon, and how they contribute to the emergent hadron mass, because these each quark is contribute to the mass of the hadrons. So this is everything that we want to understand, even that from the latest QCD, from the models, and also from the experiment. Okay, now that's about the protons. Now we look at the structure of the meson. As I mentioned, the meson is very simple. It's only even quark. It's a quark and antiquark. The pion is the light meson, and then the second one is a kaon, right? So there has a very simple structure. It's like this one, but still there's a gluon inside, which is gluon can decay to quark and antiquark, like this one. Even the 2 quarks, also this very difficult to understand at the moment. That's why this structure of the hadron attract many attention from the particle physics community, how to understand meson rather than baryon, which is baryon has a more complex structure. So as I mentioned, pions contain not only two valence quarks, but also C quarks, and which is a pop out and in of existency, so they can annihilate and create it. So pion has a gluon carrying the string force that bind the quark together inside here. So in the previous work, some people found that the gluon contribute only 10% in the pion momentum, but from the global analysis, they found gluon fraction is like 30%. So these are the result from the lattice QCD, which is the dynamics between quark and anti-quark. They can, if you remember in modern physics, if you have when they do the quark and anti-quark close together, but they cannot very close, but when they close and then after that one they repulsive, and then when they have a distance and they attracted again. So this they simulate in the lattice QCD. Also, this the calculation done by Derek Lineweber in University of Adelaide. So for the pion, we have a limited data, but we have a hope, because there will be a future experiment, you call it electron-ion collider, will be performed in US, but they will measure these things. They now is commissioning, prepare for the experiment. They will measure this again, I think to 2030. So for students, I think who interested with the hadron structure, I think they will start calculating or building the model now, and then they can predict what the experiment will measure in 2030. And also there's a compass amber in CERN, SPSS, and also electron-ion collider in China. Now this, China has invest so many, invest much money to this electron-ion collider, also in another experiment. Okay, that's what we know about the structure of the hadron and baryons at the moment. So also there's a calculation for the structure of the hadron from the lattice QCD people, which is this, as I mentioned, these are hadrons using the quantum chromodynamics in the vacuum and the free space. In this, they calculated this one like a 24/3 size with a 36 space times lattice. So this picture show the interaction between the gluon and quark in the hadron in the free space. And then QCD vacuum actually is not empty, but they has a induced chromoelectric and a chromomagnetic field, which is more complicated if you include this one, and a pure space-time in the lowest energy state, which is contrast with the empty vacuum concept that we know. And the gluon also fluctuated in short distance and on large distance. This also calculated by a colleague in University of Adelaide. And this also, but my point is, I don't want to explain this maybe more complicated to understand, but you can just see this picture, how complicated they are. I just want to emphasize that from this simulation, you can see that the complications of the gluon dynamics in the vacuum, in the free space, inside the hadrons. So it's like this one. They have pop up in, and also the gluon is pop up in, and for creating a quark and anti-quark. Okay, that's the lattice QCD and the hadron structure that we understand now. And now I'm wanna show you the prediction from the inspired model. One of them is an Ngo model. I call it that one confining Ngo model. Why is confining? I will explain later. Okay, this in Ngo model is actually is a simple model. Okay, it's a simple model which is we can using 2 flavor, 3 flavor, 4 flavor Ngo Lagrangian. This containing only local 4 fermion interaction, like this one. If you write the Lagrangian is like this one. This a kinetic part, this the interaction from the scalar, this the from the vector, and then this is the field of the quark field with the flavor component. This the Copley constant that you have to determine by feeding to the experiment, and this the Gell-Mann matrices in the flavor space, and then this the mass of the current quark mass of the up quark, down quark, and strain quark. So this information we use to this Lagrangian, and then we can able to calculate it, what they call it, all the properties of the meson or baryons. In the Ngo model, you have to understand that the gluon exchange is replaced by 4 fermion local 4 fermion contact interaction. So this gluon, if you include this gluon in your calculation, and then it's become more and more complicated. But some of them, like Dyson-Swinger equations, they also consider this one. But in this model, in the Ngo model, you can, like using some kind of this interaction, you can absorb to this coupling and then become like this one. So this become more simple because only use local 4 fermion contact interaction. But the problem is, if you use this one, this model become lack of the confinement, because there's no gluon inside, right? Because gluon is binding all the quark inside the proton and also inside the meson. So, but this also you can easily see if you look at the propagator. Propagator has, if you remember that one, like a p square minus m square divided by p square minus m square, where m square is has a divergence, which is a p square at p square equal to mt square. So this has a pole, but we have a way to cover that problem, to solve that problem. You have to regularize. One of them is a proper time regularization, but there is also 3-dimension regularizations. There is also Pauli-Pilar regularizations. But in this time, I just choose this proper time to cover the lack of the NGL model, which is lack of the confinement. And to do that one, using the proper time regularizations, and then we can introduce that what you call it cutoff parameters, which is this can be simulate a confinement. So if you see this a propagator, which is number of n propagator, and then you can write down, we translate to the proper time regularizations like this one, and then finally you can get this one. Using the proper time regularizations, and then you can see there is no the pole here. There's no divergence anymore by introduce the lambda ER, the cutoff. So lambda IR is eliminates the possibility hadron decay into quarks. It means that if you have a quark, it's a bound state quark, which is by using by applying the infrared cutoff, and then the hadron cannot decay into quarks, which also is bounded inside. So this more detail about this one you can see in paper, in this paper, in our paper, which is a 2016. And then using the Lagrangian that I saw you before, and then you can calculate the NGL gap equation, you call it. This dress propagator, this a bare propagator, and then the bare propagator interact with the vacuum inside the hadrons, and then it become another dress quark here. It should be this not pair, but it's a dress quark. So using this one, and then you can translate this one. This is the pair which is connected to the quark, the gap equation, which is MQ, which is a constituent quark mass, and then this current quark mass. This part of this the quark interact with the vacuum, and then this give you some propagator here. When you integrate, then by using this, and then you can translate this one in the proper time, and using the proper time, you can get like this one. This one is equal to chiral quark condensate, you call it. So this is a chiral quark condensate. So it means that mass is generated through interaction with the vacuum. So mass is generated by because the chiral condensate is order parameters, which is not equal to 0, which is contribute to the mass of the quark, and then is also contribute to the mass of the hardworks. So this very interesting how we explain the chiral symmetric breaking contribute to the mass of the quark. And then this is the result that we have. Now, then I saw here, this one, the current quark mass, and then we simulate using, we increase the number of the current quark mass. But in PDG, particle data groups, you can see the mass of the quark is equal to 5 MeV, but we can higher than that one. So if you higher the current quark mass like a 15 MeV, 20 MeV, and 50 MeV. And then you can see with this one solid red solid line, you can see here is the current quark mass is equal, the start from 0 and then generate the mass like this one. And then if you include that you call it chiral quark mass, and then if you increase the number, and then you can see here how they generate the mass like this one. And then you increase more, and then it's more generate mass. So this is the clearly so that the mass of the quark is generated by what call it chiral condensate. And more detail about this one is also in our paper in 2016. And this I explain more in the chiral limit, which is I have shown before, which is the chiral quark mass is equal to 0, and the constant quark mass has non-trivial solution. If you can see here, if you take this as 0, and this is it's not easy, and you have to calculate it self-consistently. And then where this one, the current constituent quark mass is not equal to 0, and then it give you some this one, which is a G pi, which is coupling for the scalar less or equal to G critical. This corresponds to dynamical chiral symmetric breaking, which is also related to Nambu-Goldson space. So this Nambu-Goldson space occurs when the chiral has a dynamical symmetry, is dynamically broken. And then if you take when the current quark mass equals 0, and the coupling is become like this one. And also there's a interpretation, which is if you take this is not equal to current quark mass, and then this is not equal to 0, this indicate dynamical mass generation is associated with the generation with non-zero chiral condensate, as that's why this chiral condensate as order parameters. So this chiral condensate also can be 0, and then if we take it as 0, and then this the scalar coupling constant is smaller than a G critical, and then we will this will known as a Wigner-Weil pace. It's not the Nambu-Goldson pace. This is another story about if you take the chiral condensate equal to 0. Okay. As you know that the meson is a bound state, right? It's not. There's no quark. You cannot find quark outside the hadrons. So it's always inside. So to do that one, as you know, in two quark scattering, in two quarks interaction, if you want to guarantee a bound state, you can you call it Bethe-Salpeter equations for the meson. For the baryon, you can using further equations, which is an interaction of three quarks. So interaction of the three quarks, these are pion, and the quarks as an intermediate state. And then you can write down this one equal to these contact interactions, and also this quark like this one, and there's another this quark become there's a loop here, which is a pion decay to quark and an anti-quark, and also this actually can be more than 1, 2, 3, and 4 loop. So in the Ngo model, we can simplify this one using T matrix, you call it, and the T matrix you can write down equal to K plus this kernel, this a propagator, this also the T matrix, and this the propagator. And the solution for this one, you can write like this one, and then simplify, and then you can reduce T matrix channel to this one. What is important from this one, and then using this reduced T matrix, and then we can define the mass of the mesons, the mass of the hadrons. So we can write down is G pi like this one, and then using this equation, and then we can determine the mass of the hadrons. And these polarizations, these come from the loops here. You can write down like this one for the pion, this for the kaon, this for vector meson. Combine with the pion and the vector meson, and then the interaction, and then you can explain the baryons. Okay, this the formula for the pion mass using the pole in the T matrix, and then you can this the pion mass, and you can write down like this one, and this variable you can define using like this one in the proper time regularizations. And also the coupling, meson coupling constant, you can get it for the pion and the kaon using by derive that one over the momentum square, which is at the Q square equal to m mass of the pion square. So for the rho meson is you can also do the same. And then what is the another important parameters that you need is like a pion constant. You can also calculate it in the proper time regularizations. The formula is look like this one. This the mass of the for the kaon, which is the string mass. This is the current quark, the light quark mass. So and then you can write down in the proper time regularizations. So these all the parameters that you need to calculate the structure of the hadrons. And then as you see many times, even that in the Lagrangian, in the calculations, there is a G pi and G rho, which is this a scalar and this a vector. And then the regularization parameters, you can determine this one by fix the lambda ER equal to 0.240 GeV, and then you can get also you can choose the mass of the quark. It is around 40 MeV, 400 MeV, and you can determine U and D dress quark mass on also current quark mass, and then from this you can fit to the physical pion mass, which is 140 MeV, and kaon is a 495 MeV, and also do the same with the vector meson, like a rho mesons, and also you can use it like a pion decay constant is 93 MeV, and then by feeding to this physical mass, and then you can get the G pi, which is 1904 GeV minus 2, and then 0, and also you can get the lambda UV cutoff, which is 645 MeV, and the mass of the string quark constituent string quark is a 611 MeV. So this range, and also the other parameters, you can calculate it. So using this one, this is really important, because when we calculated the structure, the form factor and the Parton distribution function for the hadrons, we need these parameters. Okay, now we look at the form factor in the confining in Ngo model. Before that one, I saw this picture here. So imagine these hadrons, right? In the hadrons, you have a quark, 3 quarks, say the baryons. You have a 3 quark and the other many quarks inside, and also gluons. But they moving in X, they have a X direction, Y and Y direction, and also this size is like a radius, but this impact factor, you call it B, represented by B. And then when you integrate over the X, you take the X equal 0, and then it give you some form factor, right? This is a form factor. And then if you this GPD, which is GPD as a function of the chi square, also an X. X mean is this longitudinal, and this is transverse. And then you can calculate the GPD. But in this time, I didn't explain about the GPD. I just focused the form factor and the Parton distribution function. And distribution function is a distribution of the momentum of the quark in longitudinal. This in transverse. This longitudinal. This combine of these two. So this is interesting, and then from learning Parton distribution function and form factor and also GPD, and then you can give us a more understanding about the structure of the hadron in longitudinal and transversal direction. And in the experiment, they do like this one to determine the form factor. It is the form factor, which is this nucleon, this electron, and the electron, if you put in the magnetic field, and then they decay the photon, and the electron goes that one, and then the photons hit the protons. And if you have a photon, which is a very energetic photons, and then they can, these baryons can be excited, and then you can measure another particles at the final state. So this the introductions how to understand the form factor.
Sorry if I interrupt. Just you have 15 minutes.
15 minutes.
Yeah.
Okay.
Your slides are still like 30 slides, or
yes, 30 slides. Okay, I will simplify. Okay. Thank you. Yes. Okay. So this form factor is the same things as this for the Meson is a simple one. So his Meson has a quark and an antiquark. This so you can this cartoon soon show you that photon hit the quark and then hit antiquark. Okay, so using this one, and then you calculated the form factor is like this one, and this Feynman diagram we can translate to 1 and 2, and then you can get this formula. But this using only the gamma mu. Okay, this vertex is only gamma mu, but is the gamma mu, if you use this one, you calculate it, and then when you calculate this one, and you can extract the form factor, and then the form factor form is look like this one. Okay, so it's for bare mean you have a vertex is only key this a charge operator with the gamma mu. So when you use this one, and then the result is like this one. I will skip this one because I have only 15 minutes, but I tried to reach a 15 minute. I finished in 15 minutes. So But this is not correct, because this, if you compare with the perturbative QCD calculations, is give you some like a constant, but there's it's not constant. There's a number here which is close to the running coupling constant. So we have to modify this one form factor. What we did is modify using the vertex, using like this one, gamma mu f1, which is the quark has a dress quark. Okay, using the dress quark, and then you calculated the dress like this one for the light quark, UND quark, and this for the strange quark. And then this, you call it the bubble diagram, which is I already saw you before. So you can calculate it in the proper time, and then you can get like this one. This address of the form factor of the quark. Not only so it means that the quark also has a form factor. Not only the meson or hadrons, but the quark also has a quark form factors here, which is you can see like this one. So this the quark form factor as a function of chi square, the momentum transfer. So what you call it this, and then we're using this one, you can calculate it. We using the dress quark photon vertex, and then this function is the same like a bare form factor expression. And then what you get is like this one. So you compare with the data. This the red solid red solid line is our calculations. This Dyson-Swinger equations compared to the experiment. So we find excellent agreement with the existing data and Dyson-Swinger equations, but around the chi square smaller than or equal to 6 GeV square. So this is get a form factor, and then for the this chi square times multiplying by pion form factor as a function of chi square, and you can see also it's in this regime fit to the data, but we don't have a data for the large chi square at the moment, so we have to wait the data from a Jefferson lab. Now they still analyze the data, so this could be interesting. This is also interesting to look at it. And also, if you look at the kaon, for the kaon is the formula is the same, and then this we don't have a data for kaon, and then we can compare with the empirical monopole model. So these are really fit to our calculations. And this the only data that we have in the experiment. That's why now also Jefferson lab still analyze the data for the kaon form factor, also for the pion. Okay, I will skip this one. So this only, then also we calculated the the quark sector component, which is from the string quark, down quark, up quark, and up quark in the kaon, up quark in the pion, and etc. You can also calculate it to look at what the difference between the distribution in the up quark in the kaon and up quark in the pion, right? So this is a very simple. I saw you just a simple one, but there's also for baryon is more complicated. I will skip this one. I don't. Okay, this is a Parton distribution function. Okay, there's a. So the Parton distribution function in the confining NGL model. This I already explained before. Now we calculated this one using NGL model. As form factor, we calculated using the same diagrams, which is like this one, and there's two diagrams contribute, and this the operator, and then the operator is like this one, and then by using this one we can calculate it, the valence quark and anti-quark distribution for the mesons. This we can translate to this one, and this we can translate to this one. And then using the moments, and then it can evaluate this one by using this one, where n equal 1, 2, and 3 as an integer. And then this are more technically. Okay, I hope you can read it. This using the Watt-like identity and then Feynman parameterizations, and then the final valence quark distribution in the kaon, you can write like this one. And then for pion is very simple, and then you can take like change it the strength quark mass with the light quark, and also the coupling, you can change it with the coupling of the pion. But for the pion, which is a U quark in the pion, which is equal to D quark, the anti-D quark in the pion. So this is more simple in the pion. And then once you calculate this one, you should satisfy by all these satisfy the baryon number, also momentum sum rules. So if U is equal 1 and the momentum sum rules are also equal 1, you should satisfy this one. If not, must be something wrong with the calculations. Okay. This another one. If you want to if you calculated this one, the valence quark distribution is not enough. You cannot compare with the experiment because the scale is different. So to able to compare with the experiment, you have to using the like you call it DigiLab QCD evolutions. So your calculation, you can you can evolve your calculation to more higher energy, which is the same like an experimental data. So you using this technique, this valence quark, this singlet quark, and then this quark splitting, which is the content of the quark and gluon and quark. This is quark-quark, gluon-quark interaction, and also this singlet, this gluon. So using this one, you can understand the gluon distribution function and also the singlet, the C-quark distribution function. So after you, and then this you can see here is a depend on the this one, the splitting function as I mentioned before, this one, and then the splitting function you can write down like this one, and which is a splitting function depend on the coupling, running coupling constant alpha square, and then this you can write down like this one, this alpha. As you know, this is as a QCD for non-leading order, you can write like this one. So Q, this you can see here how the definition, and then B0 is this one, and also B1 is you can write down as a function of the NC in mean color, and this is a flavor. So using this one, and then you can evolve to, you can able to compare to experiment. Okay, this result, and then you can see this the gluon distributions, this the valence quark distribution compared with experiment. This the red color solid line is for the vacuum, but also you can calculate it as a function of density. Density. If you increase density, but in here it's not too many difference. Is almost overlap, we can see here. And then if you look at the gluon distributions, this compared with the lattice QCD, which is overlap, the result is excellent agreement with the data. And also you can look at the ratio of the U quark in the kaon and U quark in the pion, and also in the free space, and also in the medium. So you can see like this one. I think if you have a quick, I didn't explain in more detail because I have 15 minutes more. I don't know how many minutes I have, but I will show you like this one. But if you have questions, maybe you can ask later. And this one for the S quark in the kaon. So this is a string quark distribution in the kaon in the free space and then density dependent. And this is a gluon distribution in the kaon in the free space and in the medium. So is this, you can see this baryon density, this saturation density. So you can calculate like this one. You can more detail about this one you can see in this paper, but this paper still we submitted to Ph.D. now still a review. And also you can look at more detail the gluon gluon ratio in the kaon, and also in as a function of density, which is you can see like this one. Okay, is this function of the x is longitudinal momentum of the quark inside the hadrons. So you can also look at the U quark ratio with the U quark in the pion, in the kaon, and then you can look at this decrease over the longitudinal momentum. It's like this one. So this one, the gluon in the kaon and the gluon in the pion, you can see like this one. And this one, I just check it for the difference of this one. So I think that I can explain. If you have any questions, you can ask later. And then I go to conclusion and an outlook. I have presented the diamyl's current symmetry breaking, which is related to emergent hadron mass and how QCD meets with the structure of the hadron. And also I saw the quark properties form factor in the ancient model. We saw the form factor on PDF, excellent agreement with the experimental data. And we saw the form factor pattern distribution function, pion and the kaon, including non-local. But I didn't explain this one. This also most interesting to look at, to include the momentum dependence of the effective quark mass, which is equal to include the gluon in the calculations. And the result is a PDF. For this one, a good agreement with the empirical data. And also the PDF, okay, this a PDF and the form factor is very useful. Nowadays, the people not only look at the proton and neutron, but it's more interesting to look at the nucleon structure, nuclei structure, which is the atom, which is like a helium, carbon, and also lead. You can also apply this one to neutrino-nucleon interaction, which is, as we know, the nucleon usually point in the calculation people consider as a point particles interactions. But now we have the structure. You can use the structure in the neutrino-nucleon interaction, and then result in more interesting. And also in heavy ion collisions, you can use the structure in the input to, as an input to heavy ion collisions. And also if you calculate it in the density, chemical potential, and also temperature, you can be able to describe the QCD phase diagram based on the QCD calculations. Okay, I think that's all my talk. Thank you very much for attention. Okay, thank you.
Thank you very much, Dr. Parada. It's a very interesting talk. I followed your talk. This is really outstanding in terms of the importance of your results, because if I understand correctly, this model, this NGL model that you apply in your work, give a consider close to experiment, yeah, close results with experiment,
Yes.
meaning that the interaction that you assume in the models are probably quite correct if compared to the old models. Yeah, so I will give the opportunity first for the attendance, respected attendance, to give some question. Yes, Professor
Yes, yes.
Tony.
Oke, bahasa Indonesia aja ya.
Oke. Iya, nggak apa-apa Pak. Ya,
Oke. Nah ini menarik nih, terutama yang terakhir tuh. Mungkin kalau Parada banyak yang poin 1, 2, 3 gitu ya. Nah saya tuh yang mungkin agak-agak nyambung yang terakhir ini ya, nuclear structure. Jadi ya dulu awal-awal prospektus disertasi saya tuh mau cerita ini, unified lah apalah, pairing phase transition in neutron star ya. Nah itu makanya saya banyak baca-baca paper itu Paulo Bedake ya. Tahu ya, Mark Alford ya, Mark Alford dan sebagainya, itu untuk yang ini Pak, apa QCD phase diagram. Nah ini
ya,
kira-kira kan di situ ada dari mulai nuclei matter sampai ke quark matter, itu kan ada love state ya, Larkin, Ochinnikov, Fuldevrel, apa kemudian 2SC superconductivity dan sebagainya, itu ya model-model itu ngitung gap equation dan sebagainya. Ini Parada kira-kira ke arah sana juga nggak? Ada rencana atau apa
Yeah,
Dulu
we
saya
just
terakhir,
yeah.
bentar. Terakhir saya punya mahasiswa dengan Pak Anto itu, tapi nggak sampai yang QCD. Kita ngerjakan ini aja yang apa outer core ya, outer core, inner core, outer core gitu ya. Cuma masukkan ini aja Lagrangiannya itu ingredientnya kita ubah-ubah, terus ada SU6, ada model-model apalah macam-macam gitu ya. Nah itu sebenarnya udah kelihatan, sayangnya mahasiswanya keburu pergi, belum sempat beresin paper gitu ya. Nah ini menarik nih, yang kaitannya QCD phase diagram. Gimana?
Oke.
Ada peluang mengerjakan?
Silahkan ditanggepin Pak.
Sebenarnya bukan hanya QCD phase diagram, tapi yang lain juga mungkin. Kalau yang tadi itu ke phase diagram sekarang itu pokoknya apa yang kalau di
condensate, Pak ya.
Kalau
2S apa campuran ya, kan?
Enggak, 2S yang Pak Tony bilang itu mungkin yang apa untuk ekstrak potensial kan, potensial dari potensial di nuclear matter. Artinya Pak Tony bisa pakai SU3 atau SU6. Tapi SU6 itu juga nggak bagus sebenarnya. Itu pendekatannya nggak begitu bagus. Makanya orang sekarang banyak menentukan potensialnya. Terkait QCD phase diagram, kalau Pak Tony mau pakai nuclear matter bisa juga pakai nuclear matter RMF model sama NGL model misalnya. Nanti itu bisa dimengerti bagaimana nukleon itu berubah menjadi quark setelah di very high density. Nah, itu sebenarnya menarik, tapi banyak orang yang udah hitung, Pak. Sebenarnya itu nggak menarik lagi buat saya. Artinya sudah banyak orang yang menghitung. Artinya orang banyak yang pakai hybrid model, artinya RMF dengan NGL. Nah, sekarang saya mau bangun model, maunya dua-duanya dari quark. Jadi nuclear matternya dari quark, satu lagi NGL quark starnya dari quark juga. Karena kan di dalam neutron star kan itu kalau misalnya density-nya terlalu besar, maka itu kan mengecil. Artinya dia di dalam fase tertentu dia membentuk namanya quark star, kan? Ya, quark star. Nah, itu jadi bagaimana perubahannya itu dari neutron star ke quark star itu yang di mana QCD phase transition ini sangat penting gitu. Dimasukkan ke dalam itu. Nah, itu tuh sebenarnya menarik, Pak.
Baik. Ini agar bisa menampung lebih banyak pertanyaan, saya buka lagi kesempatan buat yang lain. Maybe any other question, Pak Husin? Ya, Pak Husin, silakan. Profesor Husin, Alatas.
Terima kasih, Pak Parada. Lengkap sekali ya bahasannya. Cuma saya ini pengen tahu cerita populer aja nih ya. Tadi kan disebutkan old model itu ya terdiri dari, untuk yang hadron ya, terdiri dari 3 quark.
Iya.
Ya, glued by gluons, gitu kan ya. Nah, sekarang tadi kalau nggak salah di awal itu dituliskan bahwa untuk new model sekarang itu ada quark, gluon, dan sea of quarks.
Iya.
Nah, sea of quarks ini maksudnya apa? Apa sama seperti diraksi gitu?
Enggak. Sebenarnya kalau itu mirip-mirip kayak diraksi, Pak. Jadi dia itu kayak misalnya partikel yang tercipta karena ada creation. Artinya kan kalau misalnya gluon itu kalau di itu berinteraksi dia bisa decay ke quark and anti-quark.
Iya, nah anti-quark.
Nah, quark and anti-quark itu yang si quarknya.
Oke. Ya mirip-mirip ya berarti ya.
Iya, mirip-mirip. Sebenarnya kayak misalnya kita punya diraksi terus kasih energi partikel created gitu loh maksudnya.
Partikel. Ini juga mirip-mirip seperti gitu juga.
Iya, mirip-mirip. Tapi mungkin scale-nya beda ya.
Oke, iya.
Energinya beda untuk
ya.
Iya.
Jadi keunggulan modelnya itu ada penambahan asumsi ya di diraksinya itu.
Enggak menambah asumsi, sebenarnya memang itu realistik sistemnya begitu. Jadi enggak ditambah, memang dia kalau energinya cukup, gluon itu bisa decay langsung. Nanti quark and anti-quark itu bisa annihilate di dalam hadron itu. Jadi dia makanya kita nggak bisa mengerti nih, karena dia bisa created, bisa annihilated di dalam hadron. Makanya hadron itu kan masanya nggak pernah bertambah karena dia selalu popin gitu. Jadi dia konstan, tapi ada dynamics di dalamnya gitu. Makanya kita sekarang itu kita tertarik melihat bagaimana nih quark dan gluon, quark gluon itu di dalam hadron itu sendiri. Itu aja kita masih susah untuk meson aja itu sampai sekarang kita belum paham betul.
Ini munculnya model-model seperti begitu itu kaitannya dengan eksperimen yang mana? Collision, decay?
Semuanya eksperimen kan collision, Pak. Artinya kita punya ada target. Jadi eksperimen itu sebenarnya sama aja sebenarnya. Ada yang scattering, tapi ada Drellian. Artinya targetnya nggak polarized, targetnya satu terus ditembak sama beam, ya kan?
Ya.
Semuanya begitu. Eksperimennya sih sama aja, cuma teknik mengekstraknya itu nanti yang beda.
Yang bisa memprediksi ini nggak proton decay kira-kira?
Proton decay mah, kalau itu mah itu sampai kapan juga agak sulit ya. Karena
artinya possibility. Ya kan orang tetap mengharap ya bahwa proton bisa decay gitu ya.
Iya, tapi kan decay-nya panjang, Pak, karena stabil ya. Artinya kalau kita di eksperimen itu kan di eksperimen itu kan begini. Orang buat decay-nya yang cepat kan. Artinya dia yang selalu cepat bisa terdeteksi gitu loh. Tapi kalau lama gimana eksperimennya nunggu sampai kapan? Makanya nih mungkin proton decay itu nggak akan kedetek di eksperimen. Malah dia mungkin deteknya di astrofisik ya, astronomi gitu loh. Karena apa? Decay-nya terlalu lama menjadi satu phase. Dan itu juga agak susah karena di alam itu kan nanti dia berubah terus tuh. Bagaimana ngamati satu proton doang gitu? Saya juga nggak paham. Nah itu agak susah.
Maksud saya dengan model yang ada gitu orang bisa nggak men-set up eksperimen yang bisa, ya ini pertanyaan awam ya, yang bisa memperpendek lifetime dari proton gitu misalnya.
Yang mungkin bisa tapi indirectly ya.
Ya indirect maksud saya.
Ya indirect.
Seperti Higgs juga kan indirect kan?
Iya, indirect mungkin bisa. Jadi tapi decay-nya proton tuh kemana nggak tahu juga. Tapi ya karena dia harus detect di final state itu detect another particle, baru dia nanti track back ke proton decay.
Ini seingat saya istilah parton ini udah lama banget kan ya, betul ya?
Udah lama Pak, makanya itu sampai sekarang udah hampir 70 tahun ya.
Tahu kan dari ini ya Nambu ya pertama kali ya?
Bukan, parton itu orang di Stanford, lupa namanya. Dia pertama kali.
Parton itu kan quark plus gluon gitu ya?
Parton itu semuanya Pak, jadi valence quark, gluon sama tadi si quark itu. Jadi tiga-tiganya itu disebut parton. Tapi kalau valence quark doang yang 3 doang itu, tapi nggak ada gluon sama si quarknya.
Si Joseph Owens masih ada nggak atau udah meninggal, lupa? Itu
udah
kan
tua Pak.
banyak.
Joseph
tua,
Owens
ya?
Manchester University itu.
Ya FSU dulu. Nah.
Udah.
Terima kasih Pak Parada.
Prof. Husin. Satu lagi buat audiens mahasiswa mungkin atau dari
tadi ada Pak Julio tuh.
Tadi ada Pak Julio dari BRIN ya. Pak Julio dari BRIN, silakan Pak, sekalian dinyalain videonya biar lebih akrab begitu Pak Julio. Gimana Pak Julio? Ya.
Nah, ini udah on audio.
Ya. Ya, kita tunggu Pak Julio. Atau barangkali ada yang lain.
Itu menarik itu kan, scattering neutrino dengan nukleon itu kan udah bisa juga difasilitasi ya.
Bisa, itu sekarang nanti eksperimennya itu juga sekarang menarik karena orang mendetek light dark matter kan. Dark matter itu antara interaksi koheren antara neutrino dengan nukleon.
Iya. Ini tadi sudah ada Pak Apriyadi itu ya, dia dalam neutrino left, mungkin ada urusan lain.
Enggak, dia pikir saya bicara neutrino mungkin. mungkin di lain waktu kalau bicara neutrino. Saya juga melihat tertarik dengan
Pak
momen
Parada ngerjain cooling proses juga nggak? Ini kan neutrino mean free path gitu kaitannya.
cooling prepaid mah udah lama Pak. Saya
Udah lama ya.
Dari dulu saya udah kerja.
Ada yang baru nggak cooling proses neutron star?
Ini agak susah Pak. Makanya tadi saya bilang itu kalau di nuclear matter itu masalah itu masalah misalnya kita include hyperon misalnya. Hyperon itu potensialnya kita nggak tahu. Nah, banyakkan orang pakai couplingnya dari SU6. SU6 itu prediksinya nggak begitu benar gitu loh. Jadi kalau kita pakai itu, makanya orang tunggu pakai lattice QCD gitu loh. Ngitung dari lattice QCD.
Komputernya lumayan kan, bisa ngerjain lattice ya di PKNU.
Bukan PKNU nggak pakai di ini, Pak. Kita pakainya di komputer superkomputernya
Korea.
Nasional
Korea.
Nasional.
Oh di PKNU ya, itu memang resource-nya harus besar ya, harus negara itu. Nggak tahu nih siapa yang nanti kita. BRIN dulu punya klaster, nggak tahu sekarang gimana.
BRIN punya klaster, saya tahu Pak, itu klaster yang di LIPI. Saya
ya Haryo, nggak tahu masih nggak Haryo tuh.
Saya juga bilang sama Pak itu tadi ceritanya sama yang Pak Usin, yang saya bilang ke Pak Terry sama juga Mas Aryo ya, bilang supaya misalnya kan sekarang tuh mereka ngerjain yang di Atlas, kalau bisa dikembangin yang pakai lattice QCD, saya pikir menarik gitu loh, karena lattice QCD itu bisa memunculkan banyak paper, tapi sesuatu yang baru gitu, karena orang tergantung teknik apa yang dipakai, metodenya bisa berbeda gitu.
Pak Parada, nih ada yang mau saya tanyakan nih terkait non-local interaction di dalam Parton distribution function itu ya. Nah, ini maksudnya seperti apa nih Pak?
Non-local itu maksudnya dia enggaknya scalar, tapi ada misalnya ada momentum dependent gitu loh. Jadi kalau mass tadi yang saya tunjukkan di sini, tadi kan simple ya. Saya pakai massnya itu nggak ada momentum dependent ya. Tapi saya lagi ngitung untuk yang ada momentum dependent-nya. Jadi kalau kita ini massnya ini kalau kan reaksinya begini ya, kalau interaksinya begini, tapi kan di sini kan biasanya kalau antara interaksi pion ini kan decay ada gluonnya. Nah, tapi biasanya gluon juga ada juga di sini. Itu non lokal. Iya, di luar. Jadi datang dari eksternal gitu. External lake. Nah, itu kalau di-include di sini ini jadi ada kayak semacam momentum dependent di sininya, agak berubah itunya.
Jadi interaksinya tidak hanya dengan satu gluon, tapi dengan
ada gluon lain di luar ini. Dari quarknya ada decay gluon gitu loh, decay dari sininya. Dari sini tidak adanya di sini gitu. Tapi ada yang lain di sini. Di lake-nya.
Itu penambahannya apa nggak memperumit komputasi signifikan ya? Itu bisa diatasi.
Iya. Komputasinya semakin sulit. Makanya momentum dependent, kalau di-include momentum dependent-nya, maka perhitungannya ini nggak segampang ini.
Matematika yang lengkap ada kan hitungan yang loop berapa deret gitu.
Iya,
next
tapi
leading
itu kan,
order.
Ya kalau digeber pakai komputasi ini nggak kuat Pak memorinya. Ini.
Iya.
Tapi ini menarik ya. Jadi di dalam fisika ini ya, improving model itu harapannya sesuai ya. Jadi mendekati eksperimen semakin ini ya. Jadi artinya itu salah satu hasil kuncinya adanya interaksi non lokal itu tadi ya.
Enggak, itu sebenarnya gini Pak Dodi. Kan kita kan mau mendescribe sistem secara realistik kan. Sistem fisika yang realistik gitu loh. Jadi semuanya ada. Jadi kalau kita sementara kalau misalnya kita lihat hadron itu kan dia depend on energy, depend on the momentum. Kalau dia dynamics kan, pergerakannya itu ada momentumnya. Jadi kalau kita cuma ambil konstan, itu artinya kita nggak terlalu realistik perhitungannya sebenarnya.
Tapi kan ini juga mengkonfirmasi bahwa memang ada interaksi itu kan. Ya walaupun itu sudah dianggap lumrah, tapi kan penelitian ini menguatkan ya. Artinya emang jadi dalam penelitian ini memang menunjukkan bahwa itu memang nggak cuma sekedar teori kan, tapi memang benar-benar nyata bahwa ada interaksi non lokal itu kan. Iya. Memperkuat itu.
Karena kalau ini tadi saya tunjukin yang ini tadi form factor ya. Contohnya form factor tadi yang saya tunjukkan, ada Dyson Swinger Equations Model. Ini momentum dependent. Yang punya kita ini nggak momentum dependent, tapi dia describe the data sama di some region, like di sini dia bagus. Tapi untuk dimulai dari 6 itu, dimulai di 6 kita fit nih. Tapi di sini dia di sini kan agak berbeda sedikit. Nah ini karena momentum dependent. Jadi dia efeknya ada gitu loh. Di sini juga karena momentum dependent.
Oke. Ini bagus sekali ya. Baik, ada lagi pertanyaannya? Nah, ini sebetulnya sangat cocok untuk diseminarkan di forum partikel elementer Indonesia ya, grup fisika teori kali ya nanti kalau ada. Nah, baik. Kalau itu sambil menunggu pertanyaan, mungkin saya bisa bisa memberikan kesempatan untuk mungkin Pak Husin sekalian menutup Fisik Talk hari ini dengan saya tampilkan ininya.
Pak Dodi,
ya.
Punten. Mungkin Pak Parada bisa cerita dikit nggak peluang sekolah di Pukyong atau Departemen Fisik? Ya singkat aja Pak, 2 menit, 1 menit gitu. Ya.
Di Pukyong sekarang udah di Pukyong Fisik Departemen sih nggak begitu besar ya. Sekarang orang banyak perginya ke data analisis kayak gitu, kayak Monte Carlo dan sebagainya gitu. Karena apa? Karena di Korea itu sekarang kan super komputernya terlalu bagus ya. Jadi mereka lagi banyak yang berminat kalau di Pukyong sendiri banyak scholarship sebenarnya, banyak orang Indonesia juga di sini. Jadi kalau misalnya mau mungkin bisa juga. Kalau peluangnya mungkin kontak saya aja nggak apa-apa.
Ya terima kasih Pak, minimal itu ada informasi lah. Biar semangat nih. Biasanya yang semangat ke Korea yang suka K-pop ini.
Tapi di Korea itu sekarang di Pukyong, di Pusat Nasional Universitas itu banyak orang Indonesia juga mahasiswa. Tapi banyak kan kalau di sini itu banyak kan yang ngerjain yang kayak itu tadi data analisis, terus biomolekuler. Kayak gitu,
radiation physics tadi ya, berarti ada medical juga, medical physics.
Ada medical, veteriner, banyak. Ada juga.
Oke. Enggak,
ada
tadi
pertanyaan dari
Asia Nabila. Oh ya tuh.
Silakan.
Dari
Asia Nabila. Silakan.
Ya, baik Pak, terima kasih atas waktunya.
Coba dinyalain videonya kalau bisa.
Sebentar.
Nggak bisa, ya udah.
Nggak bisa Pak, mohon maaf.
K-popper.
Ya.
Nah, gimana Pak?
Ya, perkenalkan nama saya Pasha Nabila. Saya ingin bertanya yang sederhana saja. Bapak bisa tolong jelaskan secara singkat Feynman diagram itu seperti apa ya, Pak? Karena saya penasaran itu cara kerjanya bagaimana. Ya, terima kasih.
Oke. That's good questions anyway. Feynman diagram itu sebenarnya mempresentasikan interaksi sebenarnya. Jadi kalau misalnya lihat tadi Feynman diagram yang simple, ini sebenarnya simple banget nih. Jadi kalau ada scattering, katakan dua scattering. Jadi makanya kenapa orang sedang pakai Feynman diagram, karena Feynman diagram itu bisa langsung diinterpretasikan secara langsung. Misalnya begini, ini ada katakanlah ini pion, ini kan Feynman diagram nih ya. Ini kita langsung tahu nih partikelnya di sini, ini vertexnya di sini, ini vertex dengan vertex di sini. Jadi kalau dia interaction, jadi kalau kita kalau misalnya lihat ini kan berarti final state-nya di sini ini initial state-nya. Dengan using ini berarti interaksi di tengah-tengahnya ada coupling. Jadi kalau ditulis persamaannya, ini final state, terus coupling, terus initial state. Terus times intermediate state-nya, baru times yang ini final in another interaction. Ini apa ini partikel final state, terus di times couplingnya, terus di times ini. Nah, jadi ini sebenarnya Feynman diagram ini mempermudah sebenarnya interaksi yang ada. Jadi itu sama sebenarnya ini Feynman ini dibuat semacam kombinatorika sebenarnya. Jadi katakan ada dua pion. Katakan di initial state-nya ada gamma dengan proton, ya kan? Nah, kita bisa menuliskan Feynman diagram untuk pion gamma dengan proton ini, apa aja kemungkinannya. Jadi semua kemungkinannya itu kita bisa tulis ke dalam Feynman diagram. Dari situ kita bisa interpretasikan ke dari Feynman diagram itu gampang banget. Jadi bisa langsung dituliskan interaksinya gitu loh. Kalau di Feynman diagram. Makanya Feynman diagram itu banyak orang gunakan karena sederhana, gampang untuk menghitungnya gitu loh. Bisa menjawab nggak? Fasya?
Pak, punten, itu vortex itu sebenarnya apa ya, Pak?
Vortex itu artinya dia jadi kalau interaksi itu kan jadi dari final state ke dia kan berubah tuh ke final state. Jadi itu vortex itu semacam titik interaksinya gitu loh. Titik interaksi dari partikelnya. Jadi misalnya katakanlah ini ya, jangan lihat yang ini cuma ini doang nih, final state sama initial state. Jadi interaksinya itu vortex itu artinya interaksi antara partikel di titik itu gitu, antara final state dengan initial state. Jadi ini vortex ini bisa aja, kalau bisa lebih detail lagi, vortex itu kalau di teori bisa aja satu atau gamma matrix atau skalar atau matrix. Jadi dia itu satu itu artinya identity matrix. Jadi dia itu satu gamma 5, gamma mu. Kalau dia axial vektor, terus bisa gamma mu, gamma mu. Kalau dia vektor atau tensor sigma mu nu gitu loh. Kamu bisa masukkan semua itu, tapi nanti akhirnya kamu bisa vortex itu bisa itu aja dikombinasikan begitu loh maksudnya.
Ya coba kamu dalami lagi nanti di buku-buku atau bisa baca Wikipedia itu, tapi yang jelas ini menggambarkan before and after dan interaksinya begitu ya.
Interaksinya iya. Jadi makanya yang saya bilang tadi ini final state, ini initial state, tapi ada titik interaksinya gitu loh di sini. Nah, titik interaksinya itu tergantung mau partikel apa yang kamu hasilkan di final state. Jadi katakanlah kalau punya pseudoskalar itu pakai one matrix ya kan, identity matrix, atau gamma 5 pseudoskalar kalau dia identity matrix. Kalau pseudoskalar dia gamma 5, kalau dia vektor dia gamma mu. Kalau dia pseudoaxial vektor dia gamma mu, gamma 5. Sebenarnya itu semua. Jadi terus kalau dia tensor kamu bisa pakai sigma mu nu gitu loh. Cuma itu doang, itu kombinasinya yang ada.
Jadi interaksinya lengkap dalam bentuk tensor atau matriks gitu ya. Dia mengandung semua. Jadi walaupun diagramnya sederhana, tapi informasi yang terkandung bisa sangat banyak.
Banyak, ya. Karena kan Feynman diagram itu kan sebenarnya semacam kombinatorik ya, kemungkinan yang ada gitu loh, kemungkinan interaksi yang ada, iya.
Itu bisa dikonsultasi nggak Pak Parada?
Gimana, Pak?
Terima kasih Bapak.
Bahwa ada misalnya yang sebelah kiri itu quark 1, quark 2 gitu ya.
Iya, Pak.
Jadi, quark 1 mengemit gluon.
Dan gluonnya ngemit quark and anti-quark ya.
Iya, gitu ya mungkin ya.
Iya.
Tapi ini kan berarti dia reverse time ya, kalau yang in time ya, apa prosesnya ya, yang
bisa aja Pak. Nanti kan kemungkinannya kan kita ada yang bisa aja tergantung
dari forward sama backward.
Iya.
Saya mesti ingat-ingat udah berapa tahun yang lalu.
Ya, ada space like, time like, terus interaksinya yang dipertukarkan propagatornya apa?
Ya ini kan
5/2 gitu ya.
Oh enggak, kalau 5/2 kan spin.
Spin.
3/2, 5/2.
Ya, ini seingat saya nih kalau misalnya dia rata begini, flat begini, horizontal, sebetulnya kan penjumlahan antara yang miring kanan tambah miring kiri gitu ya. Yang satu itu forward in time proses, ditambah yang
satu
misalnya ini Pak Hussein, time-nya arah direction-nya ke atas nih, vertikal. Nanti dia hitung di mana mau ini final state apa ini initial state atau sebaliknya, tapi harus konsisten. Kalau enggak nanti kacau balau gitu.
Ya, ada rule-nya juga.
Iya.
Ya,
Jadi
jadi itu nanti diperhitungkan semua di matrik ya.
Iya, diperhitungkan semua. Tapi kan nanti kan setelah kita kan ada konservasi, energi konservasi, momentum konservasi. Nanti yang nggak penting-penting itu hilang dengan sendirinya.
Canceling out ya.
Canceling out, yes.
Oke deh. Baik, ya sebetulnya dari sini aja kita sudah bisa melihat gimana gambaran key quantum field theory itu ya dari diagram Feynman ya.
Iya.
Bahwa apa namanya ya itu bisa digambarkan seperti ini. Oke. Baik, kalau begitu sebelum kita finishing ini ada semacam apa namanya sertifikat yang apa namanya bisa saya share mungkin ya. Ini mungkin
saya stop share. Saya stop.
Ya.
Nggak perlu ya?
Nggak apa-apa, ini sudah kelihatan. Ya. Ya mungkin Pak Husin bisa memberikan sertifikat ini kepada Pak Parada.
Terima kasih Pak Dodi. Pak Parada, terima kasih banyak ya.
Sama-sama Pak.
Nah, ini kehormatan ini buat alma mater mendengarkan presentasi dari alumni. Bagi kami luar biasa sekali ya. Mudah-mudahan sebagai informasi, insya Allah kalau ditakdirkan tahun ini kita ada S3. Ya, nah, jadi kemudian juga kita punya fasilitas. Tadi di sini ada Pak Fauzan sama Pak Stianto ini yang mengurusi rendang, siomay, batagor, departemen. Ya, itu nama-nama server kita.
Oh, oke.
Entah kenapa dikasih nama makanan, saya juga nggak tahu nih Pak Umar.
Lontong sayur belum Pak?
Karena orang Indonesia itu paling
ya itu klaster Pak.
Ya.
Itu klaster ya. Kalau saya dulu klasternya ya nama-nama bintang, Albirio, Denip, Orion. Gitu.
Kalau nanti kerja sama-sama
jajanan.
Kalau kerja sama-sama PKNU namanya ganti jadi kimchi. Ya.
Ya.
Oke, ya mudah-mudahan nanti kita bisa minta bantuan Pak Parada ya untuk lebih mengembangkan program S3 ya.
Bisa sandwich Pak ya.
Lewat sandwich ya. Lewat sandwich program, kerjasama juga dia harus terbuka pikiran, kerjasama dengan UI, dengan ITB, ya S3 kita nanti ya. Mungkin kopromotornya keroyokan. Ya, kan itu sangat mungkin kan sekarang di MBKM ya. MBKM singkatannya?
Apa Pak?
Merdeka Belajar ya.
Merdeka Belajar, kampus Merdeka.
Kampus Merdeka Belajar.
Ya, jadi semuanya serba merdeka. Ya, terima kasih Pak Parada. Mudah-mudahan ini jadi awal yang bagus untuk terus berkomunikasi dengan departemen. Di sini juga kita banyak staf-staf muda ini yang luar biasa ya. Yang kerjanya juga keras ya, keras dan cerdas. Kalau sama Pak Umar ini seangkatan nggak ya?
Kelas.
Kelas ya.
Iya.
Pak Umar sama Yayan ya dulu ya.
Yayan Sudiana ya.
Yana ya. Itu first generation ya.
Iya.
Cuma saya lost kontak dong maka Yayan Sudiana. Okay. Dulu saya sering kontak juga tapi sekarang
kayaknya semua lost kontak itu.
Terakhir mana Malaysia ya? Terus
Malaysia Pak.
Iya.
Jadi kalau Pak Umar ini first generation, Pak Parada second generation.
Iya, second generation.
Jadi
Dodi, saya
Pak Dodi
kalau ini CS. Quarknya first generation up down. Umar.
Parada itu ahlinya sepak bola Pak.
Dulu.
Iya.
Dulu saya megang bola, Parada nggak bisa ngerebut tuh ya.
Nggak enak Pak, dosennya soalnya Pak.
Oh gitu.
Takut dapat C ntar. Kalau ngomong-ngomong second generation, Pak Dodi ini menangani second generation ya. Tapi harmonik ya, harmonik.
Sudah simetri breakingnya agak banyak nih ya. Sudah simetri breaking.
Iya.
Jadi udah ngerjainnya aneh, yang lain-lain. Oke.
Ya, ini mohon diterima Pak Parada ya, Certificate of Appreciation dari kami.
Ya,
Ya, semoga silaturahmi ini terus berlanjut. Ya, makasih Pak Dodi.
Iya.
ya, terima kasih Pak.
Pak Parada, sekali lagi kami semua mengucapkan terima kasih. Dan nanti jangan lupa untuk penyelesaian administrasinya ada beberapa form ya Pak, nanti dihubungi Bu Yesi mungkin atau tim dari kami. Oke Pak Parada, sukses selalu di Koreanya ya. Mudah-mudahan terus berkontribusi buat dunia fisika, khususnya fisika Indonesia juga ya. Ya, gimana Pak Usin?
Foto bersama.
Iya, kita foto bersama dulu ya kali ya. Oke. Saya stop share dulu. Baik, mungkin yang bagi yang bisa menyalakan videonya. Oke. Saya persilahkan untuk menyalakan videonya. Ada Pak Irmansyah, Pak Erus.
Oh, Pak Irman ada juga ya, Pak Irmansyah.
Terima kasih Parada.
Pak, apa kabar Pak?
Ya.
Saya nggak berani nanya Parada.
Ada Pak Fauzan
Enggak,
ya.
sering
Bisa
kontak.
dinyalakan mungkin itunya. Oke. Baik, ini mudah-mudahan nanti juga ini apa Pak, talknya bisa di report oleh Humas Fisika ya, dalam bentuk sebuah artikel ya. Baik, kalau gitu saya ambil gambarnya. 1, 2, 3. Baik, sudah saya save. Sekali lagi mungkin ya.
Itu ada yang upside down tuh.
Iya.
Ada down.
Oh iya.
Spin up, spin down ya.
Apa-apa, itu kan berarti dari kerangka acuan yang
Beda ya.
ya. Oke. 1, 2, 3. Ya. Oke. Baik Pak Parada. Nanti kalau sekiranya ada perlu mahasiswa mungkin bisa kontak kami ya Pak. Yang
Siap.
kira-kira
Ya.
ada topik apa yang kira-kira bisa untuk dikerjakan mahasiswa. Kami sangat senang bekerja sama dengan kakak kelas. Oke, dengan demikian kita sudahi Physics Talk yang sangat seru kali ini. Sampai jumpa di Physics Talk berikutnya. Saya Hendra Diadinata mengucapkan terima kasih kepada para pembicara dan hadirin. Semoga pandemi ini juga cepat berlalu sehingga kita semua bisa berkumpul kembali.
Iya.
Baik, terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore
Waalaikumsalam
Bapak Ibu.
warahmatullahi wabarakatuh. Selamat sore.
Terima
Terima
kasih,
kasih
Pak.
Parada.
Selamat sore, Mas.
Yuk,
Sampai
makasih
ketemu
Parada.
lagi, ya.
Sampai ketemu.
Kontak ya.
Izin live ya.
Izin lain.
Di sini ya.